Yeah.
Professor Althoefer is an experienced roboticist leading competitively funded research on soft robotics, intelligent micro-sensing system, and interaction dynamics modeling with application in minimally invasive surgery, assistive technologies, and human-robot interaction at Queen Mary University of London. He acquired in excess of 5.7 million as principal investigator from national and international funding bodies and successfully completed 22 PhD projects. Professor Althoefer's research team currently comprising 10 postdoctoral research associates and PhD students is involved in funded collaborative research with leading London hospitals, European research organizations, and international companies creating novel robot-assisted solutions for nuclear waste decommissioning, cardiac catheterization, fetal ultrasound monitoring, tissue diagnosis using miniaturized sensors, and ergonomically optimized human-robot interaction in manufacturing sector. Okay, let's welcome Professor Kaspar Althoefer's talk. Thank you. Please.
Thank you very much for the very nice introduction. Really a great pleasure to be here. It's really a pity that I have only really like half an hour and I have to drop out afterwards again. But from the discussion I just saw from the last speaker, it seems to be a very exciting workshop, and you have around 67 or so participants. So that looks very good. Anyway, I'm from the Center for Advanced Robotics at Queen Mary. And today I would like to talk about tactile perception for soft robot hands. And in my talk, I would like to give an overview of the optics-based sensor technology that we have been developing at Queen Mary, and also talk about our efforts towards integration and miniaturization of these sensors so that they are fit for integration with robotic hands, and also then to look at tactile sensing in continuum and soft robots. So optics-based sensor technology, that has been our preferred approach for a number of years now. And here we are using mainly optic fibers. And one approach is about sending light to a touch-sensitive area, a deformable area, and then measure the change in light intensity that is a function of the forces that are being applied. And so here I show this artist's impression of one of our sensors. So we have at the tip a spring, and the forces are now being applied. The spring is deformed, and that is linked to a mirror, which then changes position, is displaced. And through these pairs of fibers, in this case 3 pairs of fibers, we can measure then the movement of this mirror and can relate that to the amount of force and also the direction of force that is being applied at the tip. Here's another view. So sorry, I should go not too fast. So you can see here, for example, in the middle constellation, we have this cantilever that is experiencing an external force that changes the mirror position, and then with our optic fibers, so the light source sending light out towards the mirror, light is being reflected, and that is then received by the optical detector, and any change in force leads to a change in light intensity, which we can then detect and relate to the forces applied. So that is one of the main approaches we have chosen. We have also looked into to measure the light loss within the fiber. And I'll talk about this a bit more later. So we have here we can see another view. We have also modeled that mathematically, and then really started implementing this approach into different kinds of tools, and we have moved from very simple structures to start with. For example, here you see this structure, this cylindrical structure that has this cut here, which allows a slight bending if a force is applied, and that changes then the displacement of our mirror, and that we can measure optically. And we have integrated that into, for example, tools for the medical sector, so minimally invasive surgery, or MIS, and that allows us now to create systems like this one here, where we have a roller that can be rolled over tissue inside a patient doing laparoscopic or keyhole surgery, and we can distinguish between areas that are softer and those that are more stiff. And in this way, we want to distinguish between healthy tissue and diseased tissue, identifying tumors. And yeah, you can see that also in action. Unfortunately, the second video doesn't run, but here, yeah, you see one of those tools we have developed with the optical sensor being integrated there. So at the beginning, we achieved diameters of 10 millimeters. And so it was, oh, now it's working. Yeah, okay, so you can see now the sensor also in action here. I try to move forward, but this doesn't work. Anyway, we'll give it a few seconds. So as you can see now, we place the roller. We can roll over it, and whenever we are in contact with the tissue, we have a force signal, and that is shown on the screen in the background. So very important for us was to push miniaturization towards integration with smaller tools, and also to achieve multi-axis force sensing. And so to start with, our system was rather clunky. You see it here on top. So we are talking about 5 centimeter diameter and a huge, self-made electronic system to read out the data coming from there. So this was already a 3-axis force sensor, but we managed then to miniaturize this down to 10 millimeters. In contrast to the earlier system I showed, this is now also a 3-axis force sensor, and you can see now forces being applied in different directions lead to different signals of forces. So we can identify force and direction of force. And we also pushed that further. Our thinking here was to create tools that can be used in a medical setting, but also generally there was the idea always to create robotic hands and robotic fingers that could be equipped with tactile sensors at their tips to measure information from the environment. So this is now, I believe, around 6 millimeters, and again a 3-axis force sensor. We also developed further miniaturized systems. We brought it down to around 3 millimeter diameter. And here we have a combination of different sensors integrated that allows us to, for example, measure forces at the tip of a cardiac catheter, so a catheter that can go into the heart. So we're talking here about 3 millimeter diameter now. So the first system was a 1-axis sensor, and forces at the tip could be measured, and you can see that here in action. So we are 3 millimeters, and we were able to also create systems that had 3-axis 3-axis force measuring capability. Here, not quite the 3 millimeters we wanted to, but that was also possible in later days. So here we have actually a 3-axis force sensor that is 3 millimeters in diameter. And what I would like to highlight here is that we also were able to move forward with our interrogator. So instead of having dedicated sensors so-called key-in sensors that allow you measuring light intensity changes. We actually used a standard CCD camera. So a standard camera is being used here that observes the information brought back by the optical fibers. So you can see here camera images. You see 3 spots, each spot measuring information of of forces along one axis. And we can see that here also in action. Yep, here. It says it cannot play, but it can play it anyway. Good. So here we can see 3-axis force sensor at the tip of this catheter, and when we apply forces there, we get the light intensity sent back to the camera, and that can be interpreted into forces. In the image, unfortunately, you see only 2 points. The third one is very faint, slightly visible here. What I would like to highlight is we have a very cheap way now of actually measuring tactile force information in a very miniaturized fashion. And it's also very easily extendable because we can put hundreds of fibers towards the camera system. So here I would like to talk a bit about our attempts now to move towards the the idea of measuring forces inside a soft robotic system. And in the early case, we looked at integrating one of our force sensors inside a soft device. So here that was also part of our EU project STIFLOP, where we were developing soft robotic devices for minimally invasive surgery. And here the idea is to integrate these force torque sensors within our otherwise soft structure. And we also did some finite element analysis, but I would like to come straight to this video here. So here the sensor is at the bottom, and if you want, the problem is solved of measuring forces at the tip, but obviously it is via the soft body, and so it is not very accurate, and we need to model now our system here to relate the forces that we measure at the bottom to the tip. We have also looked into tactile sensing that could be integrated with those soft robotic devices. And here again, we apply the same approach of using pairs of fibers that send light to a small structure that can be integrated with a sleeve, a soft sleeve, that can be then pushed over our soft robotic device and is capable of measuring pressure information at various points along the structure. We were quite happy with that, but the fibers are still just flexible, not stretchable, and also the sensing element itself is more rigid than the rest of the structure. So yeah, some improvement there, but not quite there yet. I would like to also let you know that we looked into extending our camera-based idea. So we looked here at integrating array sensors, tactile array sensors into the fingertips of robotic fingers. And you have here an array of 3x3 touch-sensitive elements. And again, they move when a force is applied, and our optical pairs allow us to measure then the change in light intensity. And again, here we are using now a camera to receive the light intensity values. And here in this example, we have 9 tactiles, but you can appreciate that this can be extended to larger larger scale systems with more tactile than just an eye. Anyway, so that's here we really pursued our approach that was based on optic fibers. We have more recently also looked into light guides. And here, instead of using optic fibers, we are using transparent silicone rubber that is very suitable for integration with soft robotic fingers. And so in this particular case, we have now the soft structure, our soft robot finger. And we now again shine light through this soft material. So it is totally transparent. It keeps the light in there. However, it starts losing light when we bend the structure. And so the light intensity is changing as a function of the amount of bending that the structure is experiencing. And so we can see that here also in action. So the light is passing through the structure here, and the information is visible in the background, and so we can see how in stages now this finger is bending. And so what is really useful here is that we use the same type of material that we use to create the overall soft finger. So we are not impacting at all on the softness and the stretchability of that finger. We explore the idea of using this kind of material for to measure pressure information. And so here we have now 3 soft light guides integrated in this soft type of finger. And when you apply pressure at different points, then we can see that leads to a changing light intensity, which can be related to the forces that are being applied. I just want to make one more point before I conclude. What I also very interesting, and I think it could be interesting to further explore that, is to use actually 2 sensors to measure the stiffness of soft objects. And so here we are now looking into integrating force sensing and proximity sensing. And our approach, the approach we are using, I think is quite suitable. So we are using, again, the optics-based approach, and we use that to measure force information. So that is very similar to what I explained at the beginning. So here we have these kind of cantilever structures that allow us to measure forces in different directions. But in addition, we integrate now also proximity sensing, and that is indicated here by this section here at the front, where we have now, we apply the same approach. We use optic fibers, and instead of shining now light against a deformable surface to measure pressure information, we shine the light straight onto the environment with the idea of measuring now the distance between our fiber tips and that object that we observe in the environment, for example, the object to be grasped. And so we have developed a number of different types of fingertips, but the main idea is to have to measure tactile information through these movable objects here, or objects may not be the right word, movable tactile elements on the one hand, and on the other hand, we have our proximity sensors integrated as well. That allows us to observe the distance to nearby objects. And one clear approach is to use that, for example, in the approach, when the object finger is approaching an object, to understand how far it is before we have even contact. But I think what I find also very interesting is to explore to see whether we can use these two elements, pieces of information, the tactile information or the force information and the proximity information, to actually get an idea on the stiffness of an object that is being touched. So you can see here, I go back a bit. So we have this foamy material here, and our fingertip is now pushing inside, and the tactile sensing element is deforming slightly. So we should say force element is deforming, so we can measure forces. But at the same time, we can also observe how the distance to certain areas of the object are changing, giving us an indication of the deformation of the object. So bringing those two pieces together, we get an indication on the stiffness, or can calculate an estimation of the stiffness of the object being grasped. Good. That brings me to the end of my presentation, and I would like to thank mainly the early career colleagues of mine who have contributed to this work considerably. Obviously, the work was supported by different funding sources, and I would like to thank those as well. These days, I do not complete a presentation without mentioning that ICRA will be coming to London. So ICRA 2023 will be in London. Please take a note of the dates. Thank you very much. Thank you.
Thank you, Caspar. Thank you very much for sharing such a excellent